Now it will cover all the material covered up to 23rd. Now you have to keep in mind that subsequent quizzes will include all the material covered up to that point. So I think it will help you revise the entire course every time there is a quiz, and also help you with the final exam, which includes all the topics. Okay. So starting this lecture, so in hydrostatics or statics, the approach we have adopted is find pressure, integrate and find forces and moments. This is the approach, and then there is no motion in hydrostatics, but the governing equation is set up with reference to a natural law, which is Newton's second law of motion, with motion set equal to 0. That means sum of all external forces is equal to 0. So with a natural law, set up the governing equation, solve the equation for pressure, integrate pressure, find forces, moments. To answer his question, I don't know his name. Abhinav. Avijgyat. So we did not mention the word moment of inertia. Those are all intermediate results that may come out. We will stick to this approach. Okay. This was chapter 2 of the book. Then we went into chapter 1 of the book, talking about viscosity, Newtonian fluid, shear stresses, and the state of stress at a point. These are topics. Somebody asked me, what is sigma xx, sigma xy? These are all components of stress at a point. Stress reduces to pressure in a hydrostatic field. Sigma xx, that is Pascal's law, sigma xx is equal to sigma yy is equal to sigma rr. All normal stresses are equal in a hydrostatic field. But if the fluid is in motion, that result is no longer valid. And apart from that, you also have shear stresses. So the composite picture is represented in terms of stresses on a small fluid element. That is to be thought of as nomenclature for stress at a point. So moving on, now this is chapter 3 of the book, where the fluid is now in motion. So now you still have to find pressure, but there is one more unknown. What is it? Velocity. Okay. Now velocity is a vector. So the 3 components of velocity in 3 dimensions. Most of the time we will look at 2D problems. So there will be 2 components of velocity. So when you reduce 3D to 2D, so what happens to the third component? Either it is constant or it is 0. Okay. So, when the fluid is in motion, the procedure is, I am just trying to compare with hydrostatics, find P which is not a function of Z, it is a function of x, y and Z in general. Okay, so, then it may also change with time. It will change with position, it may also change with time. So, we show it as x t. This x with what is it? Some tilde below is vector x, x, y, z. So, find P, find u, but u is also a vector which is a function of x and t. And then last time we saw that the derivatives of u will give you the shear stresses and pressure will give you normal stresses. So, together you get the entire stress description. So, from here you find sigma. Now, sigma has a direction, it could be normal or tangential, and then it is associated with a phase. So, there are two quantities you have to specify, two directions you have to specify. So, we put two tildes for sigma and then integrate and find f and m. This m is required in some select few problems, most of the time it is f that is required. F is also force, is the force, this force usually is force acting on the solid surface. So, you have a fluid medium and then there is a bounding solid surface. So, you have to remember that fluids always come with a bounding surface. Okay, why? Because if you do not have a bounding surface, you can't contain it. Without a container, the shear stresses will simply destroy whatever configuration you try to arrive at. Okay. It's a consequence of fluids not being able to withstand shear stresses. So, there is a bounding surface and the question is find the force acting on that surface because of the adjacent fluid medium which is either in motion or is stagnant. See, this is a transition period, so I am referring to hydrostatics. As we go along, we will slowly forget hydrostatics in the class, but you have to remember it. Okay, so this is the overall procedure. So, how do you find P and U? By reference to the natural laws. Okay. Now, when you say force equal to mass times acceleration, acceleration is not 0. Okay. It's a definite value. So, set up the mathematical problem or the model with reference to natural laws, which at the continuum scale would be, so conservation of mass, Newton's second law of motion. So, also a Newton's third law of motion, which you make use of when you set up the free body diagram of the system being analyzed. And then you may call it conservation of energy, but it is really the first law of thermodynamics. And second law. The second law acts in a sort of a curious way. It sets up constraints. It tells you some things are possible, some things are not possible. So, we will see how second law comes into picture in our discussions. Now, you have done this kind of analysis in the context of solids. Of course, some of you may be doing a course on solid mechanics, where most of the time the solid is just stationary. There is nothing like solid in motion. It is not a flowing medium. Flowing is an aspect that you see with fluids, not as common in solid. So, the solid is stationary. And the second is, if you want to talk about motion of a solid object, you jump into rigid body analysis. So, it is rigid body motion. Okay. And then you apply these natural laws. So, the natural laws originally were developed for a material with a known mass content within. So, let me give you an example of how these laws are applied in a rigid body context, just to contrast it with fluids. So, let us say this is a long column of liquid, could probably contain oil, let us say, long column of oil, in which you introduce a small spherical particle, which starts to move. And I am just calling the velocity component to be u. So, initially the weight of that particle will make it go down, it will accelerate in the downward direction. Then there is buoyancy acting on it, and then there is also the stress distribution over the surface of the object because of the surrounding fluid, whose resultant, like the resultant you have calculated in case of hydrostatics, the resultant will essentially give rise to a form of resistance. Okay, why should it be resistance? That we will see later, but you can also think of second law coming into picture, that as the object is going down, the fluid exerts resistance to its motion. Okay, so, I would set up the equation of motion of this rigid particle first is m equal to constant, that is just a specified value. Mass times acceleration is equal to sum of all external forces acting on it. First is weight minus buoyancy, which is rho times some volume, this is the volume, or you can even write well, I think this is I am sorry. I am trying to write weight minus buoyancy, which is rho minus rho fluid times volume times g. Okay. So, if the material density is smaller than fluid density, then of course, this motion is not possible. So, rho is greater than rho f, and then minus, let us call this drag d, which is the force acting on the object because of the surrounding medium. The stress distribution on the solid object whose resultant in the vertical direction is d. So, this is the equation of motion that you would write, and then on starting with you need an initial condition time t equal to 0, u is equal to 0, then you integrate and get velocity. Okay. So, you get the velocity of the object. Later we will see that this equation is not very simple, because drag d itself depends on u, that you can anticipate because shear stresses depend on velocity, and pressure also depends on velocity indirectly. So, this is a sort of a harder problem to solve if you include the dependence of d on velocity. So, here we were able to apply the natural laws to that rigid object. Now, think of applying the natural laws to a fluid medium. The fluid medium is going everywhere, whether it is air, water, there are no identifiable particles. Even if you start with, let us say, you start with a vessel containing water and you drain it. So, the particles are identifiable at time t equal to 0, but later on they are everywhere, it is just flowing. So, these particles are not identifiable, which is a source of difficulty in applying natural laws to fluid systems. It is also one of the reasons why we talk of the same Newtonian mechanics, whether it is solid mechanics or fluid mechanics, but here is a point of departure. In solids, you have a well defined object that can be analyzed, maybe a beam or some column or some object or a spherical particle, cylinder rolling down an incline. But in fluids, suddenly that object is spatially distributed, spatially continuous everywhere. So, this point of demarcation makes the details very different from solid mechanics, though the founding principles that I have written here are the same. So, let me summarize by saying that in fluids cannot identify a fixed mass or a collection of particles of known mass. Okay, so, but what you can identify is a fixed volume. Okay, I just say this is my volume, that is it, the volume is fixed, and flow is taking place through that volume. This can be identified. I told you about a tank, you can define the tank as your volume. Okay. Or if it is flow through a tube, a portion of the tube is your volume, okay, and it is fixed. So, such a volume through which there is flow of matter. Okay, so, this is a fluid medium inside this volume. So, there is a flow field. Now, whenever I say flow field, there is also a pressure field. Okay, do not forget that. Pressure is always there. So, and both have to be found, U and P. Like I said in the previous slide, you have to use u and p to find sigma, from which you find the forces. So, this volume is called control volume C V, and this surface is called C S, control surface. It has a surface, and the surface is defined by the unit outward drawn normal n. Okay, so, now the particles are all going through the control volume, and since you are not picking one particle or the other, you cannot apply natural laws straight away to the control volume. But there is a very useful identity. This is the starting point of chapter 3. It lays out the identity to you. It is a mathematical identity. Why am I saying identity? It is not a natural law. It is just a mathematical, left side equal to right hand side, left hand side equal to right hand side. Okay. That identity is also called Reynolds transport theorem, RTT in short. Like Newton, one other name you encounter often in fluid mechanics is Reynolds. So, Reynolds set up the equivalence between a control volume formulation with a fixed mass, okay, or you may call it constant mass formulation. Why are we looking for this relationship? Because natural laws apply for a constant mass system. So, Reynolds transport theorem helps you apply natural laws to a control volume. That is the whole idea. Okay, so, in RTT, you identify that constant mass as the material contained in this control volume. So, Cm and Cv overlap each other at a chosen time instant, but if you think of it later, that Cm has gone somewhere else, all those particles have gone away, but Cv remains over there. But to the material in Cm you can apply the natural laws. So, let us define the attribute of the matter contained in Cv, which is Cm at time t equal to 0, the time instant of interest, Cv and Cm are the same. So, this phi is integral over Cm of rho phi, and this integral. Okay. Now, the Cv is not very small, it is a finite volume. So, rho again is density of the fluid medium. Okay. So, you have to understand that rho changes, rho is density, but it like the particle motion, rho was particle density. And there we use rho f for the fluid density. So, now here in this discussion, rho is fluid density. What is this attribute? Attributes are related to the natural law. Every natural law has an attribute. What is that attribute for conservation of mass? Mass. What is it for Newton's second law of motion? Attribute would be momentum. Is it not? What is it for the first law of thermodynamics? Energy. Yeah? So, the attributes these so this capital phi is to be linked to the natural laws, and of course, if you think of second law of thermodynamics, it will become entropy. So, mass is m, momentum you can just write it as mu. Okay. If you wish, you can put a vector. Third is energy. For energy, it is internal energy plus kinetic energy plus potential energy. G z is just symbolic of a potential, it can be any other kind of potential energy. It's here I have shown gravitational potential. I is internal energy linked to temperature. So, of course, in our discussion we are going to set temperature equal to constant, that will make I equal to constant. Constant during what? During the flow process. This flow is taking place. So, these are the attributes. So, let me write down the word associated with the natural laws. So, now you can define capital phi as the total attribute of the material contained in Cm, but Cm is Cv. So, from the viewpoint of evaluating the integral, you will use Cv, okay. But Cm is what to which you are going to apply. Cm is where you are going to apply the natural laws. Okay. Now, but Cm is going to that material is going to move out. Now, this is a slightly, it is a subtle point. We can revisit this point on Monday, that the material Cm is getting distorted and going out. At time t equal to 0, it is the same as Cv, but later on that material has distorted and has gone somewhere else. Now, how rapidly is it moving out? As rapidly as the local fluid velocity, right. So, the distortion rate of Cm is really the velocity field. So, you have to keep that in mind for understanding Reynolds transport theorem. Okay. So, this phi is evaluated at time t, then Cm is equal to Cv. Okay. Time t could be t equal to 0, but at later times Cm and Cv are not the same, but they differ to an extent that depends on the local velocity field. So, now we are trying to apply all these natural laws to a flow process where the material is undergoing changes with respect to time. These changes are in position through velocity and pressure. So, it is natural that we differentiate, look for an expression d phi dt. Okay. So, this will involve differentiating an integral. Now, you are familiar with differentiation under the integral sign. I think it is taught to you in your high school. Why do you have to think about it? Because, okay, by the way, what is small phi? small phi is thought of as the intensive value of capital phi. It is essentially capital phi per unit mass. Okay. So, that is small phi. Now, you are differentiating capital phi with time. On the right hand side, you have to remember that Cm is changing with time. So, this is differentiation of an integral where the limits of integration depend on the quantity with which the differentiation process is carried out. Okay. So, you are differentiating with time, and on the right hand side the limits of integration depend on time. And what would be the derivative of Cs with Cm with time? Will be velocity. Okay. So, what is that principle called, where you have the limits of integration depend on the parameter with which differentiation is being carried out. So, let us Leibniz theorem. So, you have to apply Leibniz rule here. Some people call it theorem, some people call it rule. Leibniz. So, this is equal to, now this is a strict application of Leibniz rule. So, this is equal to C integral over C v dV plus integral over C s rho phi u dot n ds. So, I will request you to read up the 1D form of Leibniz rule. I think it is let us say you have an integral of the form, okay, depending on the book you read, the symbols may vary. So, we are talking here alpha is just time in our Reynolds transport theorem, and the integrand depends on position as well as time. Alpha is time. Okay. The limits of integration depend on time. Okay. So, this will be, the first term is the derivative of the integrand with alpha, that is shown here on the, this is the first term. And this is the second term involving the derivatives of a and b with time, which is velocity u. Okay. So, this is a generalized application of Leibniz rule. Now, in the book they give you a detailed stepwise definition. So, we will revisit the derivation, but look at the implications of Reynolds transport theorem first. Okay. So, let us start with the first natural law, which is conservation of mass. So, if you interpret capital phi as the total mass of the material contained in Cm, Cm is constant mass system, which overlaps Cv at time t equal to 0, but is moving at a speed u. So, if capital phi is total mass, what is small phi? 1. Right, it's mass per unit mass, right. It's if I think that should be obvious to you. So, let us write capital phi as total mass of the material contained, I am not writing every word, Cm, which is equal to Cv at time t, in which case phi is equal to 1. So, substituting these, then what is d phi dt? Conservation of mass tells you it is 0. Okay. So, Reynolds transport theorem will give you 0 equal to integral over Cv plus integral over Cs rho u dot n ds. Okay. So, we have derived an equation for the conservation of mass principle. So, sometimes called the mass balance equation. So, loosely conservation of mass, mass balance equation, they are all used interchangeably. So, what does it mean? So, if you think of a flow system, the second term over portions of the boundary there is some outflow, the remaining portions may be closed, some other part may have inflow. So, u dot n, when you sum over everything, is just outflow minus inflow. Why outflow minus inflow? Because n is outward drawn normal. So, it is outflow minus inflow. This inflow can happen at various points. It is integrated over the entire control surface. Okay. So, if the two are not in balance, it will lead to changes in density of the material. You can think of a balloon and where you just have inflow, you keep pumping air, it is only inflow. Of course, if the balloon also expands, then the volume is changing. But let us say you have a vessel, I think balloon was a wrong example, let us say you have a pressure vessel. You might have seen a compressor which comes with a pressure vessel for storing gas. So, like the gas cylinder you may have, of course, gas cylinder again has a liquid phase also. But if you think of the cylinder filling process, you are sending more and more gas in. So, the density of gas inside keeps increasing. Okay. So, it has only inflow. If you have inflow and outflow, then depending on the relative magnitudes, rho may change with time or rho may remain constant. So, in general you will have, let us say a part of it may be closed, part of it may have inflow, part of it may have outflow. Okay. So, when you sum them all up, of course, corrected by the local density. So, that gives you the mass flow rate. Volume flow rate into density is mass flow rate. That will result in changes in density inside the control volume. So, here this term is broadly O minus I, and this is changes in density. Something slightly unique about this expression is that it is what kind of an equation is it? Is it an algebraic equation? Is it an algebraic equation? No. Is it a differential equation? No. So, what is it? It is an integral equation. Okay. The quantities inside u, rho, etc., those have to be found. They are all inside the integral sign. So, it constitutes an integral equation. Now, you have done what is it, mathematics for many years. I think they teach you differential equations a lot. Correct me if I am wrong. I assume that you have been taught a lot of differential equations, but very little integral equations. Is that correct or not? Integral evaluation you have done, but not integral equation. It is like saying, given the function, evaluate the integral. That you have done. Given the integrand, in this case, given the integral, here the value is 0. Given the integral, find the integrand. That you have not done, have you? That is you can imagine, if I give you some function f equal to x square and you integrate 0 to 1 is x cube over 3, you know that, and putting the limits, it is 1 over 3, that is the value. You can find I, the integral. But if I give you 1/3 and say find that function, there is no systematic way of doing it. So, integral equations are much harder to solve. So, which is a source of difficulty in this subject, that our Reynolds transport theorem gives rise to an integral equation. So, in this course, we will solve such integral equations in an approximate manner. Okay. So, we will make some approximations to evaluate the integral. Okay. So, be ready. So, that means the solution you get will also be approximate. If the integral is evaluated approximately, the solution you obtain is also approximate. So, but that is in the nature of an engineering spirit, nature of the engineering profession. Just can't get exact answers. For example, this prediction of rainfall, they keep showing you 30% probability, 40% probability. They can't tell you exactly what is going to happen. Okay, though it is a physical process, it is a fluid flow phenomenon. Okay. That is because they are not able to solve these equations properly. Okay. So, we will also solve them approximately. On the other hand, if you reduce it to a differential form, then you can apply hundreds of techniques that are available to you for solving differential equations. Okay. In a differential equation, you are given the derivative and you have to find the function. Okay. You are given df dx and you have to find f. That is a much simpler problem compared to an integral equation. So, that is one complexity here. So, we are always looking for methods to simplify this equation. The next one we will consider is momentum equation. But let us look at this equation a little more. There is a very important special case called steady state. Now, steady state is it is not always obtained, but it is often obtained. Okay. So, for example, you are told, okay, if you are maybe trains, they try to go at a steady speed. They attain a certain speed and they try to maintain that speed. Okay. You go in a bus, they go on a highway, you are asked to maintain a steady speed. Why am I talking about a highway? Where is the flow there? Flow is, the object is moving, so relative to the object there is flow taking place. Okay. So, in this room over a duration of 1 hour, did you notice any change in temperature? Overall, no, temperature was nearly constant. Okay. So, you may say the air conditioning system has enabled steady state in terms of temperature in this room. There are no changes with respect to time. Okay. At a point, this is a partial derivative, at a point means at every point. Okay. But the moment you open the door, some flow of air will take place, okay, and then transients will get set up. Okay. So, steady state is a very important special case, because then the first term becomes 0. So, then you just have integral over C s rho equal to 0, which says that inflow is equal to outflow, which is in terms of mass. Mass inflow is equal to mass outflow, that will not impact density. That is the interpretation and arises from the steady state approximation. One other important special case is an incompressible medium. What can you say about an incompressible medium? It tells you that rho is constant. So, we talked about a solid cylinder in which you are pushing in gas and the density continuously rises. So, that problem can be solved only when you treat gas to be compressible, okay, because density is changing. Now, in many problems like hydrostatics, we took density to be a constant in the liquid medium, but in air we said since it involves several kilometers distance, you can have substantial variations in density in air, but in water we said it is constant. So, like a liquid medium, so if it is incompressible, then density is constant, then the time derivative anyway is 0. And in the second integral, you can take rho out and you get the conservation of mass equation this rho is dropped. So, just take out of the integral sign, you get a simpler equation u dot n ds equal to 0. Okay, so, what does it tell you? Suppose you have a tank and now you are trying to push liquid into it and liquid is incompressible. So, there is no outflow, right. It is a sealed tank and you are just trying to push liquid into a tank. What is the consequence of this equation? The consequence is you cannot push any liquid in, because there is no outflow, if you treat water to be incompressible. But then water has a slight amount of compressibility, so you may be able to push in a little bit of water. Otherwise, in a closed vessel with just one inlet and you try to push water into it, it will keep filling up, and once it is filled up, you cannot push any more water into it, okay, because there is no outflow and you are not letting for density to change. So, the consequences inflow also will be 0. In any case, these are all integral equations. Now, what does u dot n integral u dot n ds, what does it remind you of? How much is it equal to? What is it? Correct, but in your courses on vector calculus, there is a relationship. What is integral C s u dot n ds will be equal to integral over the volume del dot u dv, correct? So, this last under all these conditions, this is also equal to integral over C v del dot u dv. So, integral over C v del dot u dv is also 0. Now, here is a sweeping statement I am going to make. In all this discussion, C v is not specified. Okay. There are several ways of looking at it. C v is not specified, therefore, if the integral of a quantity is 0 on an unspecified volume, then the quantity itself has to be 0. Okay. That means del dot u is equal to 0. That we have gotten rid of the integral sign. So, this is now a differential equation. Okay. So, we are in our comfort zone. So, what is the difference between this integral form? We have an integral form and that is a differential form. Okay. Integral form is hard to solve. Differential form, we have some experience, in fact, a lot of experience in solving differential equations. Okay. This first one, this integral over C v holds over the entire volume. Okay. It is a description over a finite domain, but del dot u, what is u? Do not say velocity, it is velocity at a point. That point, of course, is interpreted in the continuum sense. It is a group velocity of a large number of elementary particles. So, u in that description del dot u is at a point, it is a point description of the flow field, while this integral is over a pre-specified domain in the region of interest. Okay. So, I think I will stop now and just repeat that we have looked at we are getting into equations of motion. We are trying to use the natural laws. We stated the Reynolds transport theorem and we used it to derive the conservation of mass principle. Okay. So, on Monday we will move on to momentum.